Hi friends, welcome back to our Control System Simplified series. Today in this session, we'll be discussing about how to draw the Bode plots with the help of an example, a real-time example we will take for a transfer function, and then try to draw the Bode plot and understand. So far we have seen what Bode plot is in the last video and discuss about the standard factors. So today we will see how the Bode plot is sketched and led with the help of a example of a transfer function. Now let's see the steps to construct a Bode plot. Bode plot is known to have a separate sketch for magnitude and phase angle on the logarithmic scale against frequency. However, using a single semi-log graph, both logarithmic of magnitude and logarithmic of phase angle values can be sketched against logarithmic frequency. So these are all the steps to follow to draw the Bode plot. Then first write the given transfer function in the time domain form. The next identify the factors like k, poles and zeros at the origin, etc. And for the magnitude plot to determine 20 log k base 10 decibels and sketch the line on the plot. Further, a line with appropriate slope is to be drawn that represents poles and zeros at the origin that passes through the point of intersection. Omega is equal to 1 and 0 decibels. Now the point of intersection is moved to line 20 log k and draw a line parallel to the previous line. This basically adds a constant k along with the number of poles and zeros at origin. Next, the slope of this line is changed at various corner frequencies. It can also be said in a way that frequency that corresponds to the change in slope is known as the corner frequency. We'll try to understand these all the steps. Just understand each step, what is the thing, and we'll follow these steps. And basically, we'll be coming across a terminology which is called as a corner frequency. It is the frequency that corresponds to the change in slope of a curve. That's exactly all we see. Suppose if omega C1 and omega C2 correspond to the two corner frequencies when the first change in slope will occur at omega C1, while the next slope will be changed at omega C2. This depends on the factor appearing at the corner frequency. We'll try to understand this in a diagram when it comes here. Now for the time being, let's understand this example. Consider a unit feedback system. G of s is equal to 100 by s into s plus 2 into s plus 25. So, and we have to sketch the Bode plot for it. So the gain of the system G of s into h of s, we are taking as a unity feedback. So h of s is equal to 1. So G of s into h of s is equal to 100 by s into s plus 2 into s plus 25. So when hs is equal to 1, it becomes 100 by s into s plus 2 into s plus 25. So step 1 of the Bode plot design includes an arrangement of GS, HS in time constant form. First one. So how do we get the time constant from? We have to get 1 plus s form. Okay, that is exactly what we are doing here. It's 100 by 2 we are taking out. So s into 2 into s by 2 plus 1, and 25 we are taking out from this equation. 25 we are taking out. This becomes s by 25 plus 1. 2 we are taking out, s by 2 plus 1. That's exactly what we are doing here. So 25 into 250, 100, we get 2 here. Okay, so 25 4 times, and then 2 times 4. So we get 2 by s into 1 plus s by 2 into 1 plus s by 25. So this is the time domain form that we are getting here. Then further, let us identify the factors, which is k is equal to 2 here, the constant, 1 pole at the origin, because s is equal to 0 in the denominator always goes for poles. Okay, so we have 1 pole at s is equal to 0. So we have 1 at the origin. Then simple pole 1 by 1 plus s2, where t1 is equal to 1 by 2, 1 plus 1 plus st form. This is, so t1 is equal to 1 by 2. So 1 by t1 here is equal to 2. So one corner frequency WC1 will be at 2. Then the second pole, 1 by 1 plus s by 25, where T2 is 1 by 25. So WCT is equal to 1 by T2, that is equal to 25. So second corner frequency is omega 2. So we have one pole at the origin, one pole at 2, that omega C corner frequency at 2, and another corner frequency at 25. This is exactly what is the terminology that we get from when we arrange this in 1 plus ST form. Okay, so that hope this is clear. Then if we move on to magnitude plot, since k is equal to 2, 20 log k is equal to 20 log 2, that is nothing but 6 decibels. So log 2 value we can always take. So 20 into that we get 6. Okay, so 6 decibels will be 20 log k is equal 20 log 2 is equal to 6 decibels. So one pole is at origin in the previous example we have. So a straight line of slope minus 20 decibels, we will see here. We will slope minus 20 decibels per decade will pass through omega is equal to 1 at 0 decibels. This is equal to omega is equal to 1 here. This is what we have to understand. So one pole is at 0 means a straight line of slope minus 20 decibels, okay, per decade will pass through omega 1. This is omega 1, remember. Okay, at 0 decibels. This is 0 decibels. This is 0, 1. So intersection point is to be moved in 20 log k, 20 log k line. Okay, so this is 20 log k line. Here we are saying 6 decibels is here. So this is 20 log k line, red line. Okay, so intersection point is to be moved in 20 log k line, and the line parallel to minus 20 decibels per decade is drawn. This line is continued till the point of occurrence of first corner frequency, omega C1 is equal to 2. Okay, so this is exactly, this is a 20 minus 20 decibels per decade, exactly. So scale on y-axis is equal to 1 centimeter, this to this, okay, from here. This to this is 20 decibels. And 1 centimeter is equal to, from here, we are getting 30 degrees, okay. This is a 0, so 90 degrees, 30, 30, 60, 90, 120, like this, from this. So an angle we are taking as 1 centimeter is equal to 30 degrees. On y-axis, on here, this is the phase angle. We are taking as 180 as the baseline, 150, 120, 210. So 30 degrees is 1 centimeter here. Okay, so what we understand here is the intersection point is to be moved in 20 log k line, and the line parallel to minus 20 decibels per decade is drawn. Okay, so this is exactly what. So this line continued till the point of occurrence of the first corner frequency. The first corner frequency, we have seen it in earlier one. First corner frequency is 2. First corner frequency, omega C1 is equal to 2. That is extended until it is met at. So this is exactly what it is. Then let's go further. So as it is a slope for simple pole, thus will contribute minus 20 decibels per decade at omega C1 is equal to 2. At omega C1 is equal to 2. Hence, the resultant slope will be minus 20, that is minus 40 decibels per decade. Minus 40 decibels per decade. This slope is minus, because we are taking minus of minus 20. Okay, so this will be minus 40 decibels per decade. Okay, so in this way, k is equal to 1 by s, and 1 by s plus 1 plus s by 2 is added and will be continued till the point of intersection with the next corner of frequency. Okay, so the next corner frequency is 25. Okay, omega C2 is 25. And after this, it is drawn at minus 60 decibels per decade. Okay, so this is exactly what we need to understand for the for drawing the Bode plot, and that's the meaning of the corner frequency. Omega C1 is one corner frequency which the line is changing the slope from here 20 minus 20 decibels per decade. Decade means from this to this is one decade. Okay, and this to this is one decade, like that. Okay, so from this to this, we have 40 minus 40 decibels per decade, and after this is minus 60 decibels per decade. So as it is, the slope we have seen minus 20 decibels. Now, once the line is intersected at omega C2 is equal to 25, again due to simple pole, the contribution will be minus 20 decibels per decade. Thus, the resultant slope after WC2 corner frequency will be minus 40 minus 20, so that we will get minus 60 decibels per decade. And as no other factor exists, hence the final slope will be minus 60 decibels per decade here, and will be the resultant of overall GSHS. This will be the overall slope. Further, let's go to the phase angle plot and then try to understand the. So once the line is intersected at here, and this is exactly what we have seen in this. So if we see the, now I think magnitude plot is clear up to this. So we have minus 40 up to this minus 20 decibels. So this is all about the magnitude plot. And then we will see the same thing for angle plot, phase angle plot. So convert the S domain form into frequency domain. G of j omega, H of j omega is equal to 2 by j omega into 1 plus j omega by 2. Instead of S, we are replacing j omega. In frequency domain, we are converting. So 2 becomes angle 2 plus j0. So j omega angle 1. Here j omega plus j omega 2 angle 1 plus j omega by 25. Okay. So now here for constant 2 plus j omega j0 is equal to 0 degrees. So 1 by angle j omega is equal to 1 pole at origin, that is 90 degrees constant. So angle of 1 by 1 plus j omega by 2 is minus tan inverse of omega by 2, and this becomes minus tan inverse of omega by 25. So we have to draw it at for different values of omega, and 90 degrees constant, one pole because of this. And then another one, we have minus tan inverse of omega 2, minus tan inverse of omega 25. For different values, we have to draw the different omega values for 1 by j omega, 1 by 1 plus j omega by 2, and 1 by 1 plus j omega by 25. So let's see this in this graph. So phase angle table, what for different values of omega, you can say omega 0.2, 2, 10, 25, 50, and infinity. We'll calculate 1 by j omega for this same one, the 1 by j omega, and then minus tan inverse of omega by 2, minus tan inverse of omega 25. That's exactly 1 by j omega minus tan inverse of omega. So my 1 by j omega, as we have seen, it is one pole at origin, so 90 degrees is constant in this. And then we go on replacing omega values here. Since omega 1 by j omega is constant throughout, we will have minus 90, minus 90, minus 90. But whereas minus tan inverse of omega by 2, if we replace omega is equal to 0.2 in this, so minus tan inverse of 0.2 by 2 is equal to minus 5.71 degrees. We can calculate very easily. Similarly, for omega is equal to tan inverse of 2 by 2, tan inverse of 1 is equal to 45 degrees. Okay. So similarly, tan inverse of 10 by 2, tan inverse of 20 by 2, tan inverse of 50 by 2, and tan inverse of infinity is minus 90 degrees. Okay. So similarly, tan inverse of omega 25, omega is 0.2, we get 0.2 by 25, 0.45, 4.57, 21 point. So the resultant phase angle is minus 90, minus 5.71, minus 4.5. So the total we get 90, minus 96.1 Similarly, if we add these three, we get minus 139.57. Add 3. So for infinity, we get minus 90, minus 90, minus 90, minus 270 degrees. Now let's draw the phase angle for omega is equal to 0.2, 2, 10, 25, 50 on the x-axis, and phase angle minus 96, 139, 190, 220, 241, and 270 on the y-axis. This is how we will get. As we have to draw a straight line of minus 40 decibels per this, then we will have this. Initially, faint lines are drawn here from the intersection of omega 1 and 0 decibel. Further, parallel line is drawn to that line from the respective points. Okay. Now, this table, let's concentrate on this is the phase angle. So that is the magnitude plot over. Now we have the phase angle plot. Okay, so in this phase angle plot, first we have for omega is equal to 0.2, 0.1 is here, 0.2 somewhere, so minus 90. How much we are getting 0.2? Minus 96.16. So minus 96.16 is somewhere here. Omega is equal to 0.2. Then for next value, for omega is equal to 2, minus 139. For omega 1, 10 here. So this is a logarithmic scale. We will have 1, 2, 3, 4, 5 up to 10. Okay, so omega 2 somewhere here, and we will have 139 degrees here. This is in the minus scale. Then omega 10, for omega is equal to 10, minus 190. Omega 10 minus 180, this is minus 190. Omega 25 minus 220. Omega 25 will be somewhere here, and this is minus 220. Will be somewhere this point. Then omega is equal to 50 here. You will get omega is equal to 100 somewhere here. So omega 50, we have minus 241 somewhere here. And then omega is equal to infinity constant, we'll have minus 270. Minus 2, and this will be a continuous straight line from here. So this is exactly what we are seeing about the desired plot sketched for the given transfer function of the control system that represents the magnitude as well as the phase angle against the logarithmic frequency. So this is exactly what we do for plotting or for drawing the Bode plot using the transfer function. So hope that is clear. Thank you very much.